Okay. Sorry. Okay, so let's see. Let's talk. Before we go on to today's the main part of the lecture, let's talk a little bit about the midterm. Okay. We've already published the grades for the midterm. Okay, so you can go on Panda Grader and see what you got. Let me just give you some of the statistics for the midterm. So it was out of 120. So that was the max score, and it was literally the max score. Okay, the mean was 63, and the standard deviation was 22.5. Okay, now let me just give you sort of a summary of how people did. So I tried to go through and say roughly what constituted. This is extremely rough. You shouldn't take it too seriously, but it's sort of a guidance for you if you want some feedback. I'll give you this sort of numerical guidance. Sorry, can we settle down? Okay, so I'll give you this kind of numerical guidance, but then I'll also try to give you some guidance in terms of what you might learn from the midterm and what I learned about you from the midterm, right? So where we are and where we are going, etc. So it should be, I hope, useful for you in terms of evaluating, sort of understanding where we are going and understanding where we are so far and so on. Okay. Sorry. Can we settle down there a bit? I mean, if you want to have a conversation, maybe a whisper. Okay. All right. So let's see. Okay. Again, you should take all this with a bit of a grain of salt because it's very, very approximate. But roughly, if you want to understand where you stand, if you got above 82, then you should think of it as some form of A. It's A minus A or A plus, right? So some form of A. If you got above 51 but below 82, then you should think of that as some form of B. If you got above 32, you should think of that as some form of C. And if you got below 31, then that's some form of D or F. Okay. Just what does this mean in terms of distributions? Well, there were roughly 120 of these. There were roughly 230 of these, roughly 110 of these, and roughly 50 of those. Okay? Right? So that's sort of one way of looking at how you did. Now, Okay, so what does this mean in practical terms? Well, if you're in this group, you should feel extremely happy. If you're in this group, you should feel rather happy about where things are going. You're doing reasonably well, and obviously you can do better, and so on. Now, these lines are pretty approximate out here. So somewhere around here, somewhere around here, that you're in some trouble, and you have to do something radically different. So what can you do that's radically different? Well, certainly we are more than happy to help you in any way in trying to figure out how to navigate this course better. But that's going to require, if you're anywhere close to this, below this boundary, or even close to this boundary, even if you're sort of in the 35 range or 38 range, you should look at how you feel, how much you understand, but it's time to do something, take this very seriously. And taking it very seriously involves many things. So one thing that it involves is maybe you're just not studying that efficiently. And it could be possible that instead of putting in, maybe you're putting in all the effort you need to, but you're just not being very smart about what you're doing. In which case, Well, you can certainly do it by introspection. You can come by and see us, meaning the TAs. You can come see me, and we'll try to help you in any way that we can, right? The other possibility is that you're just overextended, in which case you have to do something radical. Radical meaning you have to make more time, either by dropping some other course, making up more time, or dropping this course, and that'll give you a lot more time. Right? But you have to do something about it. Right? So what I mean by being serious is you've got to make sure that you have the resources, the time, the effort, the will, the motivation to do well on this. And then that's not enough. You've got to also be smart about it. And being smart about it means also coming by and getting some feedback about what you're doing. So now let me say a little bit about. So I'm going to go through a few things. I'm going to go through a few of the questions and tell you what kind of thinking it took to solve those questions, and then I'll draw some kinds of general conclusions about what kinds of skills most of you have learned or should have learned by now, and where we are going with this course. Okay, so let's look at examples first, and then we'll talk in more generalities. Okay, so I'm going to skip questions 1 and 2. Well, those are sort of more, they're somewhat more straightforward to understand. At least they're multiple choice or short answers. I'm also going to skip question 6 because, well, most of you were not supposed to attempt that question. So we are really left with 3 questions that we're going to talk about. And I'll sort of try to tell you what are the different strategies you could have followed and what would have constituted an acceptable answer, just so that you get to see what the mindset is and what was required and what was not required, because I think there might be some misconceptions about that. Okay, so let's start with question 3, which said, n-dimensional hypercube. And you have to show any cycle must have even length. Okay. So how do you approach it? Why should any cycle have even length in the hypercube? So what were, there are different strategies by which you can prove it. One strategy would say something like this. Remember what the vertices of the hypercube are labeled with. So vertex of the hypercube is labeled with an n-bit string. So it might be labeled with 1, 0, 1, 1, 0, 1. Okay, so that's what it's labeled with. Now, every time you take an edge from this vertex, what you're doing is you're flipping one of these bits. So maybe you flip this bit in going from here to here. And so the label now is 1, 0, 0, 1, 0, 1. Okay. Now, what can we say about this? So now this, the cycle, okay, this path sort of goes on, and eventually it's got to double back and come here. Now, one thing you can say about it is the only way you can come back here is if this bit becomes 1. Now, along the way, what you've got to do is this bit became a 0. Well, it might become a 1 again. So let's say it became a 1 here. It was it was something ... 1 ... we don't care what that is. It became a 1. And then maybe it became a 0 again. Maybe it became a 0. So you got ... 0 ... But then it has to become a 1 again because it can't come back here otherwise. So it's got to go back to ... 1 ... Okay, so how many times does this bit flip? Well, it's got to flip an even number of times. It goes from 0 to... it went from 1 to 0, 0 to 1, 1 to 0. Okay, 0 to 1. And now it's back here, and these bits might flip in order to come back here. Right? But whatever happened, this bit flipped an even number of times. But the same is true for every other bit, right? And so you have an even number, if you watch just this bit, it flipped an even number of times. If you watch just this bit, it flipped an even number of times. All these are edges on your path. And every edge on your path is of this form, and therefore the total number of, and each type of edge is used an even number of times, therefore the entire path is of even length. Okay, that's one proof. Okay, so that's proof number one. So let's call it bit flips. Okay, so each bit is flipped an even number of times. And each such bit flip is an edge. Right? That's the property of the hypercube. Right? You're just flipping bits in order to move around in the hypercube. So that was one way you could think about it. There were the most common other way to think about it was in terms of parity or distance. So you start from x. Okay? Now you could sort of say, well, what happens? Well, you have that's what x looked like, 1 0 1 1 0 1, and then you flip a bit and you went to 1 0 0 1 0 1. Now you can say something about these two strings. Here you can say, well, this has an even number of ones, and this has an odd number of ones, right? And the claim is every time you move, you go from odd to even or even to odd, right? Because you're flipping exactly one bit, right? If you had four ones before, now you have either 3 or 5. If you have 3, now you have got to go to 2 or 4. But regardless of which one, you're going from even to odd to even, right? Each time you're doing that, you want to come back to even. How many times do you flip? Even number of times, right? So you keep bopping back and forth between even and odd and even and odd. You keep doing this until you go back. So how many edges are there? There's an even number, right? Yeah. So each edge goes from even to odd, or odd to even. And so, right, you've got to go back to, if you started from even, you've got to go back to even, so you need an even number of vertices. Okay. Now, of course, if you really wanted to do an induction, you could say, by induction on the length of this, after every step, you switch parity. After an even number of steps, you're on this side. After an odd number of steps, you're on that side by induction on the length of the path. Okay, so that would have been a formal proof. So if you want to do this formally, you would do an induction on the length. And you'd be saying, by induction on the length, after, if you go for k steps and k is even, you're on the even side. It's odd, you're on the odd side, and so on. Right? That's something you could do by induction, and that would be a formal proof. Now, of the people who got this using this argument, nobody actually gave a formal proof. However, we didn't take any points off for that. Okay? So why didn't we take points off for that? Well, because, first of all, it would have been very discouraging. Right? But secondly, this is something I've been emphasizing in class, that, proofs are not just lifeless objects. They're not just syntax. It's not just the fact that you write base case, induction hypothesis, induction step, and then it's done. There has to be an idea in the proof. And here was the idea. Right? So if you got the idea, that's good. That's great. You've already taken a big step towards writing proofs. And, there's no reason not to give you full points for that because you've taken that big step. That's a marvelous thing. Right? And so that's where we are. In this midterm, we were grading it from this viewpoint that, did you take these steps towards, the essential steps towards writing proofs? And many of you did, and that's what we graded you on, which is a great thing. So you should feel good about it. You should feel good that you've managed to, understand these aspects of writing proofs. That's an excellent thing. And as you go forward, once you understand what the main idea of a proof is, and you can play with that, you will in the next step you'll start understanding how to write formal proofs or more formal proofs. That's okay. Some of you will, some of you will understand only up to a certain point, and that's okay. That's where we are going to in this course, right? And okay, so now there was a different proof by induction that there was one person who got a different proof by induction which was perfectly correct, but I won't go into it because it was somewhat more complex. It was a very nice idea. It's actually not even that complex, but I just don't want to. It was an anomaly. One person really thought about it. It was great, but there were many of you who tried to fit a proof by induction, but without an idea, and that didn't work out so well. Okay, so in other words, if you were sort of saying, well, let's try an induction, let's write base case, induction hypothesis, induction step, but without having a picture of what you were doing, and then actually, you sort of navigated and you painted yourself into a corner. Well, then that didn't go so well. Okay, so let me describe to you what this false proof was like and why it was really a dead end. Okay, so what some of you did was you said, well, look, your n-dimensional hypercube you can write as, it's two n-1 dimensional hypercubes. So there's the 0 subcube and the 1 subcube. Okay, now you have your cycle. So we are doing an induction on n. So n is the induction on dimension. Okay, so these are two n-1 dimensional hypercubes. And then you say, well, look, if you have a cycle in the n-dimensional hypercube, what must it look like? Well, there's a part of it here, and there's a part of it here. Okay? And then you said, well, the part of it here must look like a cycle, and the part of it here must... Well, no, that's not what you said. Okay, what did you say? I'm not even sure I can reconstruct it. But, okay, it was something like this. You start with a cycle in the n-1 dimensional hypercube, and you start with a cycle here. And now, obviously, you want to join them together, so there must be a vertex here which is right opposite that one. So you connect them, and then the neighbor must be right opposite, and so you take out this edge and you connect them. And now you say, well, this was an even number of edges, this was an even number of edges. You subtracted 2 and added 2 to that, so you still get an even number, QED, or you proved that in the n-dimensional cube you had an even cycle. Right? So what's the problem with that? Why is that not a good proof? In fact, why is that a terrible proof? Right? So if you were trying to show that you understood induction, why would this be the thing that you would never do? So what's the major principle of induction that this violates? Yeah. Yeah, so it's a buildup error. Or it's this fact that when you do induction, if your induction hypothesis is about n-1, then to deal with the case n, you start with the case n. You don't start with n-1 and build up to n-1 and build up to n, because then you run into trouble, right? As we did here. Because what did we not consider? So you must start from n. Okay, so if you were genuinely starting from n, you would say, okay, so here's my n-dimensional hypercube. It consists of two n-1 dimensional hypercubes. Okay, so far so good. So far we didn't say anything different. And now we say, we have a cycle in this. What does a cycle look like? Well, maybe it looks like this. You went along for a little bit, and then you crossed. Then you went along for a little bit, and then you crossed again. And then you went along for a little bit, and you crossed again. Right? And you may cross many, many, many times, right? There's nobody who's stopping you from crossing as many times as you want. And you might do that, or you might cross more times if you want. Okay, now I challenge you to find me a cycle here. Or a cycle here. Right? It's just there's a path here, and then you teleported to this side. Then there was a path here, then you went to this side. But there were, these might be far apart, right? So all you have is these fragments of paths on each side. How do you apply an induction hypothesis to that? Right? There's no cycle there, right? So no even length, and right. Whereas if you looked at it like this, you sort of said, well, we started with a cycle here and started with a cycle here, and then we took out these. But this is not what was given to you. What was given to you was a cycle in the n-dimensional hypercube. Right? Does it make sense? Okay. Let's talk about the stable marriage problem. So for A, which was worth the majority of the points on that problem, and what it said was, let P sub j of M be the rank of the woman that M proposes to, right? So you have M here. He has a list of women, and on the jth day, maybe he's proposing to this woman. So the rank is I. So P sub j of M is I, right? That's who he's proposing to on that day. Right? And what we did was we summed up P sub j of M over all men M. So we have fixed a day, J, and we've said, what is the rank of all the women who are being proposed to on that day? Right? So you have M, M prime, etc. Each of them have their ranks of women they're proposing to, and you add up this plus this plus this plus this plus this. Okay? That's the left-hand side. Now on the right-hand side, you say, for each woman, how many men did she already reject? Right? So you take sum over all W of R sub j of W. Right? So how many men did each of the women reject? And you wanted to say, this minus this is a constant, is some constant value independent of j. And why is that? Well, these were the men rejected on any day up to the jth day, meaning on days 1 through j minus 1. Okay? Well, so how do we reason? Well, on day number 1, nobody is rejected. So day 1, no one's rejected, but everybody proposes to the first woman on their list. So this, the first summation is equal to n, the second summation equal to 0, and so the difference is n. But then from then on out, what happens? Well, the only reason a man moves on to the next woman is because somebody rejected him. Okay, so that's all you had to say. You had to say, well, every time a man moves forward, this is because somebody rejected him. So you add 1 to this side and you add 1 to that side. Right? So it all stays constant. Every rejection adds 1 to this summation and adds 1 to this summation, so the difference always remains constant. Right? That's all you had to say. Right? So the proof was every rejection involves exactly one man, so increases summation over M of P sub j of M by 1, and it also increases this by 1, and summation over W of Rj of W by 1. Okay, that's it. Okay, so again, the interesting thing in this proof was just understanding what the main idea was. The main idea was understanding that every time someone gets rejected, it increases this sum by 1 and this sum by 1. In order to understand this, you have to understand the algorithm itself, right? So it was testing. Did you understand the algorithm? Did you have a picture of it? If you did, it was very simple. You just understood that rejections, are symmetric. Whenever a man gets rejected, a woman must have done the rejecting, so both cancel out. Okay, I'm going to skip on to number 5, which is a counterfeit coins. Okay, so this said you have 3 to the n coins. One is lighter, and you want to determine which one in n weighings. And so this really involved that you write out a recursive program, and the recursive program was very easy, right? It was, you divide into 3 groups, 3 equal groups. So you have 3 to the n minus 1, 3 to the n minus 1, and 3 to the n minus 1. You weigh this versus this. If one of them is lighter, you know that's where the lighter coin is, the counterfeit coin is. If they're equal, you know it's here. So now what you have to do is recurse, right? So if you're saying counterfeit S, and then you divide into S1, S2, S3, right? In the 3 cases, what you're going to do is you're going to, if whatever you're going to call counterfeit S1 or counterfeit S2 or counterfeit S3 in each of those 3 cases. That's what you do, right? And now you prove by induction that this works because, prove by induction because this is a smaller number. You know that it works correctly. You know that it takes n minus 1 weighings, and therefore this one works correctly, and it takes n weighings because you did exactly 1 more before this, right? So that's what you had to do. Again, the important thing was getting the idea right, and then saying, ideally getting a little bit of the proof right by induction, right? That's what you were being graded on. So let me try to summarize now what the takeaway from all this is. Okay, so. So first of all, we've been grappling so far with this whole idea of what's a proof, right? So what's a proof? And a proof, as we said, it comes in many flavors. It's, you write it at a certain level of formality, okay? But as I've been trying to emphasize in this course, you do not get a proof without having an idea. Right, so embedded in your proof is an idea. You've got to have an idea. Otherwise, just writing something formally down is not very meaningful. Okay, and certainly in your exams, we look through. Almost nobody, very few of you actually wrote down formal proofs, and that's okay for now. Right, it takes a while till you're able to write down formal proofs, but what we wanted you to do is at least write down the idea carefully. Okay, and that's what many of you did, and that was great. And those of you who didn't, you should really learn how to write out that main idea in the proof. Okay, and then if you can take steps beyond that and say, well, not only is this idea, but here let me break it down further and say it more carefully. Well, that's good. So we were saying, how carefully do you state the idea, but without really necessarily requiring you to write it down very formally, because that's a lot of steps. Okay, the second thing that came across, I think, in all of this was there's something that you have to, maybe you should think about as you are, as you work on this course. So the second thing you should think about is group work versus individual work, right? So you'll notice that on your homework, you work in groups, versus in the exams, you have to work individually. right? And so, make sure you're not running into a problem where you think that, as you're working in a group, you have this false sense of confidence that you really know how to solve problems, and then you get to the exam and you realize maybe not, right? So how should you sort of protect yourself against that? Make sure that you're not running into that situation. So this is where you have to realize that the way homework is supposed to work is not that you work in groups. It's that you work in groups to brainstorm. But then what you're supposed to do is go home, think about the answer by yourself. You have to have the picture by yourself, and then you write it down by yourself. Right? That's an important part of it. Now, of course, you could be cutting corners and thinking, well, nobody's going to catch me if I don't do that. That may be true. But then when you get here, you have to, you really have to work on it individually. And if you have not written up the answers by yourself, you never know whether you really understood it or not. It's very easy to think, while you're in the group, to think that you really understood and you were really solving things, and you don't know how many of the steps were being done by you and how many by other people, right? It's a learning process. It's a great thing, but you shouldn't be misusing it, right? So it's a very simple thing, but you should pay attention to it as you do it. Okay, so that's one thing. The second thing that you might find interesting, and you can, if you do, you can certainly request that your TAs do this. So there are some who might do this, which is in your section. So given that you have so few opportunities to work individually, maybe one thing that some students find useful is having a 5-minute quiz at the beginning of the section where there's some simple question that's given to you, and then you try to work it out by yourselves. And then whether you turn it in or not, that's completely immaterial. So it depends upon what you'd rather do. You could just try working on it yourself, and then at the end of 5 minutes you're told what the real answer is, and then you can determine for yourself, are you really understanding enough to work things out by yourself? So if you are, then you could be more confident about your abilities. If you're not, then you know that you've got to figure out, you've got to think about these things a little bit more. Okay, so those might be takeaway messages from this. So by and large, I think you should be happy with how you did. Those who shouldn't be happy should be very unhappy with what they did, but they have ways of dealing with it, regardless of whether they would like to continue in the class or not. So if you'd like to continue with the class, do come and see us, and we'll try to help you to the best of our abilities. If you don't know what you should do, again, come and see us, and we'll try to advise you. And if you know exactly what you want to do, go ahead and do it. Okay? Is that helpful? Any questions? Yes.
Yeah, so for the hybrid question, right, you said the second one was not a formal proof, but
Which?
Is that the same kind of cases?
Yeah. So neither of these was a totally formal proof, but you could convert it into a formal proof. And from our point of view, it was close enough, right? And actually, for each of them, different students did, spelt it out into different levels of detail. Where for some people, they spelt it out in enough detail that it was clear that they knew what they were talking about, regardless of whether they wrote it up formally or not. For others, they wrote it out in a sketchy way where it was either unclear or it was clear that they didn't have the full picture, but they had the germ of the idea. So we sort of said, okay, you have the germ of the idea, you get this, partial credit for that, but obviously there's some confusion about some part of it, right? So that's how it was graded. Yeah. Okay. Any other questions? Yeah. I'm sorry. You wanted to know about 4B. 4B was the second part of this, which said, I don't know if it said this. It said something like, well, show that there must be some person, some man or some woman who is matched to somebody in the top half of their list, right? And so there's a small calculation involved, but let me tell you the intuition behind it. The intuition is the men are starting at the top of their list, right? So in order for every man to get to the bottom of their list, they've got to be rejected by at least n over 2 women, right? Each one has to be rejected by at least n over 2. That's the only way none of the men qualify to get somebody on the top half of their list. But now remember, the men's loss is the women's gain, because every time a man is rejected, by the improvement lemma, a woman moves up in her list, right? She always keeps moving up every time she rejects somebody, right? So now, if all the men get rejected at least n over 2 times, then the women together move up by n over 2 times n steps, right? The only way this can be is if one of them moves at least n over 2 steps, right? So one of them is going to move into her top half if all the men move down into their bottom half, right? So that was the proof, and now you could actually do I more or less did the calculation for you, but you could also word it in terms of P sub j and R sub j if you wanted to. Yeah.
What if they all ended up in the middle? Then that wouldn't be in the top half. I mean, for me, that was the issue when I came about.
I think if they are exactly half, then for the men not to be in the top half, they've got to go one beyond the top half, so they got rejected that many times. And the women, moved up at least n over 2 times, so they're starting from the lowest one, but if they move up n over 2, they've gone already beyond the halfway point. Okay, so it's just enough for them to move across. Yeah.
Would you start enforcing formality at some point?
Yeah, so the question is, would I start enforcing formality at some point? What I would be, of course, that would be grand if we could do that, right? What I would be very happy with is if people understood how to make a good, rigorous argument, not necessarily formal, where they state their ideas clearly, without necessarily making them completely formal. Right? That's already, that would be a great thing. And actually, if you can get to that point, you should feel very proud of yourself, because that's a real breakthrough. Then you've accomplished a lot. Okay? So there are two different parts here. You can go for rigor, you can go for formality, you can go for both, of course. But already if you go for rigor, you're doing extremely well, and I don't mind if that's where you go. Right? Okay. More questions? Okay. Any feedback? Anyone want to say how you feel about the thing, or any other comments? Yeah? Yeah.
Can we get more time on the next session, or at least have a shorter exam?
Yeah, so I'll definitely try to make an exam where time is not a constraint. I think maybe this one got away from us a little bit, in the sense that we really thought of 6 as a completely optional question, which which you wouldn't even try if you didn't have the time. And then I think it was a bit surprising for us that it ended up, with 2 hours, it still ended up being such a close shave. So, okay, but the expectation is so it may have been a slight miscalculation on our part in terms of the length, but the goal going forward was to make sure that time was not an issue, and then it was a bit of a surprise to us that even leaving out 6, it was that close. Yeah.
How many people actually did 6?
Well, the max score was 120. Yeah. And then there were, then there was 119, 118, etc. So there were people who really did try, and so getting all 6 to within, to within getting a couple of points off, or few points off, 4 or 5 points off. There was a number that, it was actually populated all the way down. So, yeah. Okay. Okay, so Sorry, there's one thing I should say. If you did get, if you did get below this threshold, you should really come see. Well, there'll be instructions. Maybe we'll have an email to you saying, come see the head TA or one of the other TAs. And then after you talk to them, if either you feel or they feel that, you should come talk to me, please do. And if you, so I just want to make sure that all the people who were below that threshold really figure out what they're going to do. The other, I'm sure I don't have to remind you that drop date is tomorrow. And so if you do plan to do something about it, that's, you should come by and see us before that, so you actually get advice. So we'll be around tomorrow, trying to give you feedback and help you understand what your options are. And, okay. Yeah.
Is there a point recovery policy?
What's a point recovery policy?
Like, if you do really well in the final, you get some points back.
Yeah. So the question is there a point recovery policy of the sort, well, if you do extremely well in the final, then you get points back for this midterm? So, in principle, I don't have a problem with that. I think that if you did poorly here and you really want to try to make up, that's a great thing, and I'd like to encourage that in any way possible. On the other hand, I don't want to create an automatic formula saying, well, we take we take the max. So we'll replace midterm 1 with midterm 2 if you did better, because then that's equivalent to saying midterm 1 is worth, instead of being worth whatever it is, 20%, now we make it 10% and midterm 2 worth more, right? So if we wanted to do that, why didn't we do that in the first place, right? So I think I'll have to figure out how to do this so that it, so that it's meaningful and equitable, and right. So I would really like that people who are trying to understand, have every incentive to do that, and we don't, grades and points, they're only worth so much. What's worth, what this course is really about is learning and how much you actually understand at the end of the day, and what you go out with, right, from this course. And so that's what I'd like to maximize, and I'm going to think about it and figure out how to make the policy reflect that. Okay. And any other questions? Comments? Okay. Yeah, that's... Okay, so maybe let's move on and let's talk about the next topic in this course, which is RSA. Right, the Rsa Cryptosystem. Okay, so what we're going to talk about now is bijections, Fermat's little theorem, and the Rsa Cryptosystem. Okay, so first let's talk about bijections. So what's a function? Everybody here knows what a function is, but let's sort of define it in a slightly different way. So let's say you have the function f of x equal to x plus 1 mod n. So let's say n equal to 7. So now this function looks like this. So you have the domain, which consists of the points 0, 1, 2, 3, 4, 5, 6. Right? It maps this set A. And then you have the range, which in this case happens to be the same set A. Okay, so in general, it'll be a set B. B happens to be equal to A, consists of the set of points 0, 1, 2, 3, 4, 5, 6. And you have the function f, which maps these points to these points. And how does it map it? Well, 0 goes to 1, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 6, and 6 goes to 0. Okay. Now, the fact that this is a function, okay, this happens to be a particular kind of function. Okay. The fact that it's a function just means that every point here should be mapped to something, which means the fact that it's a function means that the out degree must be equal to 1. So every point here must have an arrow pointing out of it, exactly one arrow pointing out of it. It can't have two, otherwise it's not a function. Right? If 3 had 2 arrows pointing out from it, 1 to 4 and 1 to 1, that wouldn't be a function. Right? Because you wouldn't know what the value at f of 3 is. It could be 4, it could be 1. That's not a function. It's got to be a definite value. Okay? But now, let's say you have a function g which maps b to c. Okay, and maybe c is just g of x equal to x mod 5. Okay? So now what happens? Well, c is 0, 1, 2, 3, 4. And now 0 gets mapped to 0, 1 gets mapped to 1, 2 gets mapped to 2, 3 gets mapped to 3, 4 to 4, and 5 gets mapped to 1, and 6 gets mapped to, 5 gets mapped to 0, and 6 gets mapped to 1. Okay? So this is still a function. The out degree is still 1. But the in degree doesn't have to be 0. It doesn't have to be 1. It can be 2 or 3. Right? You can have collisions on this side. So the in degree can be greater than 1. We can also have h which maps c to mod 8. So now you have 0, 1, 2, 3, 4, 5, 6, 7. Okay, and now you go 0 goes to 0, 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4. And these guys have nothing coming in. And it can be 0. Right? All these are possible. It could be 0, it could be greater than 1. It doesn't have to be exactly 1. Okay? This picture is very special. It's called a bijection. Okay? Where all the in degrees are 1. Okay? What it gives you a one-to-one map. You know, it gives you a correspondence. Right? It says 0, 0, it pairs up elements in these two sets. It says 0 here is identified with 1, 1 is identified with 2, 2 with 3, and so on. It gives you just a correspondence between the two. Okay? That's called a bijection. Okay? There was a question? Yeah.
Is the bijection the function, or is it like?
It's a function. So this function f is called a bijection if it has exactly this property, right? So what's the property it has? Oops, I painted myself into a corner. So let's start on this side. F is a bijection means that the in degree on this side is 1 for every vertex. Another way of saying that is it has two properties. One, no in degree is more than 1. Okay, so if f of x equal to f of y, like here, well, the only way that can be is if x equal to y. So here, f of 0 equal to f of 5, and so there's a collision. That's not a bijection, right? So we'll say bijection is 1 to 1, meaning no degree is bigger than 1. And the way you say that is if f of x equal to f of y, then x must be equal to y. Right? If two things collide, there couldn't be two things. It must be the same thing. Right? So there are no collisions. Right? The other property is it's onto, meaning the degree must be bigger than 0. Right? So for every y, there exists x such that f of x equal to y. For every y in B, there exists x in A. Right? If f is a function from A to B, for every y in B, there's an x such that f of x equal to y. Now, something that you can see here is if it's a bijection, then you can also, if you're looking at the function like this, the other thing you can do is you can also look at it from this side and you can say, well, this is being mapped back to that. Right? You can look at the function either forwards or backwards. Okay? So we can say, well, if there's a function f which points this way, then there's also a function f inverse that points that way. And if f maps x to y, then f inverse maps y back to x. It just takes the operation that f does and it undoes it. Right? Is that clear? So if you have a map, so f is a bijection means f maps A to B is a bijection, means that there's also a function f prime which maps B back to A. And it has the property that it undoes what f does. So meaning for all x in A, if you look at f of x, and now you apply f prime to it, you get back to x. Right? So you start from here, you apply f to it, you go from 2 to 3, and now you apply f prime, which is, you just take this backwards. So almost by definition, you go back and you're back at 2. Right? So you if x is 2, you apply f of x, you get to 3, and then f prime just takes you back from 3 to 2. So you're back at 2. Right? The other thing you can do is, it's an inverse. That means that for all y in B, if you start from B and you apply f prime of y, and now you apply f to that, you get back to y. So you start from 3, you apply f prime, you go back to 2, and now you apply f, you go back to 3. Right? It's sort of clear, right? It's obvious. That's what it does. Right? So now these two conditions, the existence of f prime, the fact that f prime exists, which undoes what f does, this is equivalent to saying that f is a bijection. So theorem, f is a bijection if and only if there exists f prime such that these conditions hold. Right? That f prime undoes what f does, f undoes what f prime does. Right? Yeah. F prime is also a bijection. Okay. Is that clear? I suspect that most of you have seen this already, but it doesn't harm if you see it again. And okay, because we are going to use it in a much more interesting fashion now. Okay, so what we are going to do is we are going to look at probably the most famous bijection in computer science, which is called the Rsa function. Okay, this is one of the most basic functions in cryptography. The Rsa cryptosystem, and all it is a bijection. It's a bijection that's built on the properties of primes. So that's why modular arithmetic, right? So this is what we are going to get into. We are going to understand what happens when you work modulo a prime or modulo a product of two primes, right? And there are very beautiful properties that these numbers have. And then what we are going to do is we are going to use it to define a bijection, which has particularly nice properties. In fact, it has such nice properties that whenever you buy something from Amazon and you're sending them your credit card number, you had better use this bijection on it, right? You use RSA on it to somehow make sure that nobody who's listening in can figure out what you're doing, what your credit card number is, or what your, what this secret information is. Okay, so let's try to understand something about the Rsa cryptosystem. So in the Rsa cryptosystem, you have two large primes, odd primes. Okay, actually, if you have large primes, they are necessarily odd. Okay, so you have two primes, P and Q. They're prime. Their product, P times Q, is equal to N. Okay. Now, in the Rsa cryptosystem, what you're trying to do is you're trying to send a message. Okay? So your message is M. And M happens to be between 0. It's a number between 0 and n minus 1. Okay. Is everyone happy with a message being a number? Why would you send a number as a message? Okay, certainly you would send a credit card number as a message, but what about in general? Would you ever send a number as a message? I'm sorry? In binary, right? ASCII. You could use any kind of encoding, and numbers and sentences. It's all the same thing, right? Text and numbers, they're all the same thing for computer scientists. So sending a number, it should feel completely natural to you. That's a message. Okay, your message is a number between 0 and n minus 1. Okay, so now how do you send this message? What you do is you want to make sure nobody understands it. So what you're going to do is you're going to use a bijection. Okay, what's it a bijection on? It's a bijection mod n. So it's on the numbers from 0 to n minus 1. Right? It's a bijection which maps the numbers from 0 to n minus 1 to the numbers from 0 to n minus 1. In such a way that somebody who looks at your bijection applied to M has no idea what M is. Okay, it scrambles up the message. It really changes it in some fashion that makes it very hard to understand what M was. Okay, so this is called the encryption function. So you have the encryption function E of M. Okay, and this is going to be, let's call this X. So X is also going to be a number between 0 and n minus 1. Okay, so E is a map. It maps the numbers mod n. So it maps 0 through n minus 1. It maps it to 0 through n minus 1. Okay, so 0, 1, 2 up to n minus 1 to 0 up to 1, 2 to n minus 1. So you take M and you encrypt it. You apply this encryption function. Okay, what's this encryption function? Well, it's something very simple. Okay, so it turns out that there are two different numbers, E and D. So there's E, which is the encryption exponent, and D, which is the decryption exponent. And these are used to compute this function E and the function D. Okay, what's the function D? Well, you send this message across to somebody, and now this other person has to decrypt it and get back the message M. So what they do is they apply D of X, and lo and behold, they get back M. Okay? So D is the inverse of E. Right? It's like F and F prime. Right? So you apply E to encrypt the message, and they apply D to decrypt the message. Now let's see what E of M and D of X are. So E of M is just M raised to the power of E mod M. Okay? And D of X is X raised to the power of D mod M. Okay, that's what it is. Okay, that's the Rsa cryptosystem. Okay, now these D and little e are cleverly chosen, and we'll learn how to cleverly choose them so that it has the property that once you compute E of M and then you apply D to it, you get back M. Okay, so the property it has is D of X is just D of X is E of M is equal to M. Right? Okay, what's another way of writing this? Another way of writing this is E of M is M raised to the power of E, and then D of that is this thing whole raised to the power of D mod N. So what this tells us is M raised to the power of E times D is congruent to M mod N. Okay, so that's the magic property of RSA. Okay, they figured out you're working mod, a product of two primes. There's a magic way of picking E and D, these encryption and decryption exponents, so that no matter what message you start from, if you raise it to the power of E and then raise it to the result to the power of D, you get back the message itself. Okay? That's their claim to fame. RSA stands for the inventors, Rivest, Shamir, and Edelman. Okay, this was a brilliant scheme. Took them a long time to come up with it. Okay, but it's absolutely beautiful. Okay, and it's incredibly useful. Okay, so what makes it so useful? Well, let's talk a little bit about that. So, what makes it useful? So this is one of the very first so-called public key cryptosystems. Okay, this was invented back in 1977. Just a year or two before that, this whole notion of a public key cryptosystem was invented. Okay, and this was a big thing. So cryptography goes back centuries, right? Certainly Caesar used cryptography, and there's a Caesar cipher, but it goes back, really far back, and it's extremely important. It's used in many, many things. It's used, of course, in financial transactions. It's used in affairs of state. It's used everywhere, right? Privacy, security, this is an extremely important thing. But then, back in, I think, 1975, something happened which had never happened before in cryptography. This was the first time in history that you could say something, that there was a possibility of doing something, which before that you would have thought it was impossible to do. And the thing that was possible here was that if you had two people who had never met before, they had never ever met before, they could still communicate secretly with each other without somebody else who was listening and figuring out what they were talking about. Okay, this is the public key aspect of it. Okay, so in cryptography, it's always the same cast of characters. There's Alice and Bob who want to talk to each other, and then there's Eve who's the evil eavesdropper who is trying to listen in. And Eve is extremely, she's extremely devious, she's extremely smart, okay, and she has a lot of time on her hands. And Alice and Bob, they're your regular people. They have lives, they have things to do, and what this public key crypto system does is it allows them to, stay ahead of Eve. Even though she can listen in on the wire, she can snoop around, she still doesn't understand what they're talking about. And in fact, she can't even understand that, even though Alice and Bob haven't met before, right? So. They just found each other on the internet. They are trying to communicate with each other. Eve's trying to listen in. That's, of course, the scenario when you're trying to purchase something from Amazon. Of course, you don't know Amazon, right? All you know is their website. So there's no chance for you to exchange secret information and say, well, when I say XYZ, I really mean ABC, right? That was the nature of cryptography in the past. Right, before this, but public key crypto systems changed all that. So how does it change that? Well, you see, the way it works is, so in this case, think of Bob as, well, I guess A is Amazon, is it? Okay, so think of Alice as Amazon, right? So she has this, she picks this number n, which is a product of two primes, P and Q. Okay. Now, she knows P and Q. Nobody else does. She took these primes, she multiplied them together, she got the number n. Now here's a fact. The fact is that even though we know how to generate primes, very large primes, like a few hundred digits long, in a fraction of a second you can generate them on your on your laptop. You can generate these large primes, you can multiply them together very quickly. But then once you've multiplied them together, nobody knows how to take them apart. Because to take them apart, you'd have to take this number, which is a few hundred digits long, and you'd have to break it up into its prime factors, P and Q. But that's like looking for needles in a haystack. There's just this needle P and Q, and it's a huge haystack. It's an exponentially large haystack. You could try looking at possibilities till you're till the end of the universe, and you won't have enough time. If this is a large enough number. So it's very easy to make up this large number. It's very hard to break it apart. So now Alice has an advantage over everybody else in the world. Right? Nobody else in the world can possibly figure out these secrets, P and Q. So now how does she leverage it into something that allows Bob to communicate with her without Eve figuring out what it is? Okay, so what she does is she picks the encryption and the decryption exponent based on P and Q. So she needs P and Q to figure out E and D. So she picks E and D, and she keeps D secret. So D is secret. Once she picks E and D, she can even throw away the prime factors P and Q. Okay? So she doesn't need the prime factors anymore once she's done picking E and D. Okay? So she picks E. E is easy. Usually you pick E equal to 3. That requires a certain constraint on P and Q, which we'll talk about later. But E is easy. Think of it often. E is often 3. Okay? But D is what's hard to generate, and for that you require the prime factors P and Q. So Alice uses the prime factors P and Q to figure out D. At that point, if she wants to, she can throw away P and Q, or if she wants to, she can keep them for sentimental reasons. Okay, now D she keeps secret. Okay, so she throws away PQ, she keeps D secret, she publishes N and E on her website. So N and E, these two are public. These are not only public, they are published on her website, so everybody knows what they are. This is secret. Okay? So now, notice what happens. Since these are secret, when Bob has a message to send her, he can take M and he can encrypt it. To encrypt it, he takes M, he raises it to the E, mod N. All that's easy. That's the encryption of M. Call that X. So this is what he sends to Bob. Sorry, he sends to Alice. Alice, meanwhile, Eve, meanwhile, is listening in on the line. She snoopes, she figures out what X is, but she has no idea what M is. Okay? Because she doesn't know how to go from M to the E back to M. That's a very difficult thing to do. As far as we know, in order to do this, you actually have to factor N. She doesn't know the factors of N. Okay? But Alice knew the factors of N, and she actually was clever enough to figure out this decryption exponent D, which makes use of the factors of N. So now all she has to do to recover the message M is take X and raise it to the power of D mod N. This is something she can do easily. And lo and behold, she gets back M. And that's the message. Okay? So a priori, we would have said, Alice and Bob never met. How could it be that Bob is sending a message and Alice has an advantage over Eve? Okay? And if you were to think in terms of information, Alice has no advantage over Eve. But then you think computationally, you think, well, N is public, so in principle, everybody knows the prime factors. It's just a matter of sitting down and factoring it. But on the other hand, computationally, it's very, very hard to factor. So even though Eve could, in principle, factor N and figure out P and Q, and then figure out D, and then compute M, in practice, she cannot. In practice, to do this would take her well beyond her lifetime, maybe even the lifetime of the Earth, maybe even the lifetime of the solar system. So these numbers can get very large very quickly, and so the guarantee you have that Eve cannot listen in is sort of ridiculously, it's a ridiculously secure system by the time you're done with it. Okay, it's probably compromised because maybe Alice left these primes sitting around because or the exponent. So this is how computer security actually works. The things that break down are no longer the cryptography. It's that people leave their passwords lying about, or they're not secure, etc. Right? So, okay. So that's the Rsa Cryptosystem. Now, let me say a little bit about how the Rsa Cryptosystem works. And okay, so what is it about primes that I'm sorry, we only have a few minutes left, so I'm not going to work through an example in class. I'll just tell you about why it works, and then, certainly there are examples worked out in the notes, and then we'll get to examples next time in the next lecture. Okay, so for now, I'm just going to back up, and I'm going to give you a little bit of a taste of why this works. Right? It should all seem very mysterious to you. So let's spend 5 minutes talking about what it is about primes and modular, working mod a prime or working mod a product of two primes that's so magical. Okay? So the magic of all this lies in what's called Fermat's little theorem. Okay, so I hope you realize that in order to have a little theorem named after you, you also have to have not a big theorem, but a last theorem. Is that what it's called? Yeah, it's Fermat's last theorem, isn't it? Yeah, okay. All right, so, but this little theorem is really beautiful. It's little, but it's very powerful, even though it's little. Okay, so what it says is, suppose you're working modulo a prime. Okay, sorry, can you see up here? So remember what RSA, the reason RSA worked was let me write that down in this corner here so you can compare it to Fermat's little theorem. The reason it works is you have these magical exponents e and d, so that you choose any message m and you raise it to the power of e times d, and you get back m mod n. Right? Where n was p times q. Okay. Now Fermat's little theorem is a building block of this. Fermat's little theorem says, suppose you are working mod p, and p is a prime. Right? So what it says is, if p is a prime, then for all a raised to the power of p is congruent to a mod p. Okay? So I hope you can see that there's some similarity between these two. And in fact, this is the main building block that allows us to say that this is true. So we'll figure out from this what E and D should be so that this will turn out to be true. Okay. Now, there's another way of saying this. So what is it about primes that's special? Well, you have... There are only two types of numbers mod a prime, right? There's 0 mod the prime, and then everything else has GCD 1. The greatest common divisor between a and p must be 1 if a is not 0. Right? Because if a is 0, it's a multiple of p, then it's not relatively prime to p. But since p is a prime, anything else is going to be relatively prime to it. It has greatest common divisors 1 with it. So another way of saying this is, if GCD of a and p equal to 1, then a raised to the power of p minus 1 is 1 mod p. Okay, so that's the form in which we'll actually prove Fermat's little theorem. And then once we prove it, okay, we'll then understand why this is really, just with a little bit of work, just by putting together P and Q, we'll figure out why this property holds. And that's the construction of the Rsa cryptosystem. Okay? Now, the proof of Fermat's little theorem is again one of these proofs where it's really a bit of magic. Okay, so you look at it. We'll go through it next time. You look at it, and the thing to do there is to look at it and say, you just have to marvel and say, how did somebody think of that, first of all, and secondly, you'll follow it. You'll follow every step, and then you'll say, but that's remarkable, right? That really shows that it's true. I mean, you'll follow every step of it. And it's going to be simple. There's nothing complicated about it. And yet it's going to be difficult to wrap your mind around it. Okay, so we'll do all that next time.